Hello, welcome to the remaining part of the random process. Today we will discuss the receiver model for angle modulation, calculation for figure of merit of angle modulation, signal to noise ratio calculations, noise in phase modulation, noise in frequency modulation systems. Regarding the receiver model of angle modulation, as we already have seen in earlier classes, that the demodulator is having the intermediate frequency filter at its input, which is receiving the signal, and the signal is already mixed with the additive white Gaussian noise. The processed signal is fed to the limiter, where limiter plays an important role in the receiver, which limits the amplitude fluctuation which is introduced by the channel, because channel has a additive noise which mainly works on the amplitude of the angle modulated signal. So though the signal is residing, that means message is residing in the frequency content, the amplitude fluctuations will introduce little bit phase error at the receiving signal. So limiter is a circuit which will chop out this amplitude nonlinearity which is present in the receiving signal of the angle modulated signal. Thereafter, this signal is passing through the de-emphasis circuit. Now, before going to discuss about the de-emphasis circuit, let us see what happened in the modulator circuit for which de-emphasis circuit is required. Prior to the modulation of the frequency modulated signal, the signal undergoes another process known as the pre-emphasis. Why it is required? Because for the voice signals, normally the magnitude deteriorates when the frequency goes into the higher value. That means for any baseband signal, more is the frequency, the amplitude will be less in the spectrum. That is why the amplitude should be boosted up in the higher frequency domain so that the full bandwidth of the frequency modulated signal may be utilized. So therefore, the magnitude of the higher frequency component is amplified prior to the modulation in the frequency modulator circuit by means of pre-emphasis circuit. That is why here in the receiver, after demodulation, there is a de-emphasis circuit exists that will re-establish the original message content which was pre-emphasized. And after the de-emphasis circuit, whatever is the raw message has been obtained will be low-pass filtered with the which is limited by the bandwidth equivalent to the message bandwidth, and the signal is sent to the output. Normally here the receiver model in the noise analysis of angle modulated signal, which is shown in the adjacent figure, it employs a device which is opposite to the pre-emphasis circuit known as the de-emphasis circuit. The intermediate frequency is also another important parameter. It is required to realize these filters at lower frequency level, because more is the frequency, more will be the cost of realization of the filter as well as amplifier. That is why the frequency is reduced by the IF filtering, and that is why the carrier frequency is reduced to a lower value, and the corresponding circuits, that is the remaining circuits in the demodulator, are designed in the lower frequency domain so that the cost of realization may be reduced as well as the circuit complexity may be reduced. The figure of merit calculation for angle modulated signal is shown here. As we know, the figure of merit is one of the important factor for the receiver. That is why the figure of merit calculation is always important when you are designing a good quality receiver. At the beginning, the mathematical expression of the frequency modulated signal shown, where the phase content is the integrated part of the message if it is a frequency modulated signal, but if it is proportional to the message, then it is a phase modulated signal. So that is why angle modulated signal is normally written as the phase content in the carrier signal So if phase is directly proportional to the message, means it is a phase modulated signal, and if it is the integrated part of the message, then it is the frequency modulated signal. So this is the little difference exists between the frequency and phase modulation. Now when it is contaminated with the noise, we can consider the in-phase and quadrature component of the noise. The quadrature component dies out because of the sine component, which is negligible if the phase content is very small. So therefore the pre-detection will be strong if the carrier amplitude is much larger compared to the noise part, and weak prediction will happen for in the signal to noise ratio if the carrier magnitude is very much small compared to the noise signal. The signal to noise ratio calculation as shown here, it considers the phasor diagram which is shown on the right hand side. This phasor diagram is important because the hypotenuse shows the resultant of the magnitude of the frequency modulated signal. Here the phase content is nothing but the angular deviation due to the superposition of the noise content. Therefore theta t, that means the phase content of the demodulated signal, determines the content of the message magnitude. And finally the demodulated signal is proportional to the slope of the phase content, which is shown Vt equal to kd by 2 pi into d theta dt. So this is the output of the frequency detector that shows that the output voltage is proportional to the message content, because theta is the integrated part of the message. So once we differentiate the phase content of the demodulated that is frequency detector output, then we can get the output is proportional to the message content. The noise in the phase modulation can be derived in the similar fashion. Only difference is that in the earlier case the frequency detector was utilized. Now here it is a phase detector. In the earlier case we have derived the slope of the phase detector output, because the phase content of the frequency modulated signal is the integrated part of the message signal, whereas in case of phase modulation the output is the phase which is proportional to the message. So here phase is directly proportional to the message, so no need to find out the differentiation of the phase detector output. So that is why we can directly get the output which is proportional to the message content. The noise for phase modulated signal detection can be further continued for the power spectral density calculations. That is, power spectral density of the in-phase component and the quadrature component are derived, and thereafter the signal to noise ratio uh, found for the output section of the phase modulated receiver. For the input of the phase modulated receiver, we are getting another part of the signal to noise ratio. If we take the ratio of the signal to noise ratio output and to the signal to noise ratio input, we are getting the expression for the phase modulation figure of merit, in which it is clearly showing that it is equal to the square of the Kp, which is the phase content. Kp is the phase content, and Kp square of the Kp multiplied by the mean square value of the message signal. Now this mean square value of the message signal is nothing but the message power. So once we amplify the message prior to the modulation, then this mean square value of the message could be increased. So therefore the figure of merit could be increased. So once we are getting the phase modulation index with higher value, or the message power with higher value, we can improve the receiver figure of merit parameter. The noise in frequency modulation can be further written as Vt is equal to, this is proportional to the differentiation of the phase at the output, which is having Kf into Kd into Mt plus Kd by 2 pi Se into dNs dt. Now again, letting Kf into Kd equal to 1, we can adjust our scale to unity so that we can have the output voltage is proportional to the message. So therefore the output signal is the signal power is the mean square value of the message, and the noise at the output of the filter is the slope of the uh, noise signal, that is NSDT. Therefore the power spectral density of the noise can be easily found, where from that is it is useful to derive the noise power at its output. The noise power for the frequency modulation can be further carried out. The calculation shows that how we can find out this noise power at the frequency modulator output. So noise spectra at the frequency discriminator output is a bowl shape. So more is the frequency, gradually the power spectral density increases. Therefore, within the message spectra, we are getting the shaded portion of the power spectral density. So therefore, the figure of merit can be easily found out for the frequency modulated signal at the receiver output, that is SNR output by SNR input, provides a figure of merit, which is finally calculated at the bottom. There are certain problems which can be discussed now. In an amplitude modulated signal, the received signal power is 10 to the power minus 10 watt. That means when the signal is received by the amplitude modulator, signal is received, the power is very small. The order is 10 to the power minus 10 watt, with a maximum modulating signal frequency 5 kilohertz. So therefore, message bandwidth is clearly 5 kilohertz. The noise spectral density at the receiver input is 10 to the power minus 18 watt per hertz. Now, if the noise power is restricted to the message signal bandwidth only, then find the signal to noise ratio at the input of the receiver. So signal to noise ratio at the input of the receiver is nothing but the SNR input. So that is the question we have to find out, what is the signal to noise ratio at the input of the receiver. Now here one thing is very much clear, that signal power is given 10 to the power minus 10 watt, but the message frequency is 5 kilohertz. So if the noise is dominating the signal bandwidth, then it is obvious that if we multiply the noise power spectral density with the message bandwidth, we can get the total amount of noise power at the input of the receiver. So this is one of the important calculation which is required prior to the uh, demodulation, because signal to noise ratio has two components. One is the signal to noise ratio at the input of the receiver, another part is the signal to noise ratio at the output of the receiver. So once we here the question is to find out the signal to noise ratio at the input of the receiver. Therefore here we have to find out the signal power and the noise power separately, and we have to take the ratio to find out the signal to noise ratio at the input of the receiver. So signal power is clearly showing that 10 to the power minus 10 watt is the signal power, and the noise power can be easily derived by multiplying the noise spectral density, which is 10 to the power minus 18 watt per hertz, with the message bandwidth, because here it is clearly showing that if the it is clearly told that if the noise power is restricted to the message signal bandwidth only, therefore noise power can be easily found out by multiplying this 5 kilohertz into 10 to the power minus 18 watt per hertz. So since 5 kilohertz, if we convert kilo into 1000, that is 5000 hertz. So if we multiply it with 10 to the power minus 18, so it will be nothing but 5 into 10 to the power minus 15 watt. It is 5 into 10 to the power minus 15 watt, because hertz cancels out once we multiply. And if we take this as a denominator to the signal power 10 to the power minus 10 watt, then the ratio is 10 to the power minus 10 divided by 5 into 10 to the power minus 15. So once the denominator 10 to the power minus 15 goes up with the numerator, it will be 10 to the power 5. So 10 to the power 5 divided by 5 is the required signal to noise ratio at the input. So 10 to the power 5 means it is 100,000 by 5. So it is the 20,000 signal to noise ratio at the input of the receiver. The next question is that how does a pre-emphasis circuit provides extra noise immunity? Normally, we know for frequency modulated signal, the message signal is normally acoustic vibration. That means the voice signal. Now, for the voice signal, we know more is the frequency, less will be the power, and especially for the musical signal, high frequency content is dominating. Now, since musics are having high frequency content, they are having lower magnitude, but they are significant. So that is why pre-emphasis means the boosting up those high frequency component is essential, especially for musical signals. So that is why pre-emphasis is a common process which is employed in the frequency modulated signal, so that the input message signal higher frequency component may be boosted up prior to the modulation, and once it is boosted up, thereafter uh, the frequency modulation is carried out. Now, frequency modulated signal cannot be demodulated and fed to the transducer, because frequency demodulated signal are the pre-emphasized message signal. So that is why before being applied to the receiving transducer, this demodulated signal need to be de-emphasized. That is, the reverse process of the pre-emphasis has to be carried out after the demodulation of the frequency modulated signal. So therefore, extra noise immunity is provided by using pre-emphasis by boosting up the higher frequency component of the message signal. The next question is, in wideband frequency modulated system, the output signal to noise ratio increases. So the question is, in wideband FM system, the output signal to noise ratio increases or not? That is the question. Yes, it increases with the square of the bandwidth, because the signal to noise ratio calculation for the wideband FM system shows that uh, if we find out the expression, mathematical expression that shows the output signal to noise ratio is proportional to the square of the FM bandwidth. So that is why we can say the output signal to noise ratio increases with the square of the bandwidth. The next question is, the use of pre-emphasis and de-emphasis in an FM system improves the noise performance over which frequency range? Now, this is an important question, because in case of frequency modulated signal, sometimes pre-emphasis and de-emphasis uh, not required also, because voice signal has normally lower magnitude at higher frequency component. But if the voice signal is already having a sufficient magnitude in the high frequency component, why should we require pre-emphasis or de-emphasis? So that is why, if there is such a situation that higher frequency component is having the lower magnitude, then only we need to boost up the higher frequency component, and that is why we can say that it improves the noise performance over the higher frequency range. That is, boosting up the message signal at higher frequency range, we can improve the signal to noise ratio for the FM signal using pre-emphasis or de-emphasis. The next question shows, in a receiver, the input signal is 100 microvolt, while the internal noise at the input is 10 microvolt. With amplification, the output signal is 2 volt, while the output noise is 0.4 volt. Find the noise figure of the receiver. So the question is important because it requires the expression of figure of merit of the receiver. We know the figure of merit of the receiver is nothing but the ratio of the signal to ratio at the output of the receiver to the signal to ratio of the input of the receiver. Now, as the magnitudes are given for signal and noise for the input and output of the receiver, we can assume that since the resistances are not given, we can assume the resistance are of unity ohm. Therefore, squaring the signal only, we can say we are getting the normalized power. Therefore, signal to noise ratio can be found out by the ratio of the square of the signal to square of the noise signal. So in this way, signal to noise ratio at the input means 100 microvolt square divided by 10 microvolt square. Similarly, signal to ratio at the output of the receiver means the 2 volt is the signal magnitude, so square of 2 means 4, and the output noise is 0.4, so we have to take the square of 0.4 and take the ratio 2 square by 0.4 square. That is the signal to noise ratio at the output of the receiver. So in this way, whatever the two expressions, that is two ratios we are getting, if we take the ratio of those two ratio, then we can find out the figure of merit of the receiver. Now the next question is, the receiver is operated at a temperature of 300 Kelvin. The transistor used in the receiver has a average output resistance of 1 kilo ohm. The Johnson noise voltage for a receiver with a bandwidth of 200 kilohertz is what? The question is, you have to find out the Johnson noise. Now, as we know, the expression of Johnson noise, which is given on the right hand side, the square of the RMS current, RMS noise current divided by bandwidth is 4k into T divided by R. So K is the Boltzmann constant, capital T is the ambient temperature in absolute in Kelvin, and R is the resistance. So R is given, Kelvin temperature is also given, the bandwidth is also given, delta F is 200 kilohertz, resistance given. So we can easily find out this ratio, that is mean square current divided by the bandwidth. This is the noise voltage, the Johnson noise voltage for the receiver, we can easily find out. Thereafter, the question is, a resistor R equal to 1 kilo ohm is maintained at 170 degrees Celsius. The RMS noise voltage generated in a bandwidth of 10 kilohertz is what? So here noise voltage equation is clearly showing the square root of the product of the 4 into resistance into Boltzmann constant into temperature in Kelvin and the bandwidth. So all these values are given. So replacing this with the numerical values provided in the problem, we can find out easily the RMS noise voltage. Thank you.